In this discussion, we're going to be looking at volume and how it relates to the net change theorem. So as our little discussion here, let's let V of t denote the volume of water in some reservoir at time t. All right, so it helps to have a picture. So let's suppose we have, here's our reservoir, and we have some water in here. And what we're going to be doing is we're going to be pumping water in. Ooh, try that again. So some water can come in this way, and then we have a little spigot on the end here where water can be pumped out if needed. So we have this tank of water, and water is coming in and water can go out. And and there might be some controls here, but we have this tank of water where there's some way to get water in and some way to get water out. And so what we're doing with this function v of t is we're just describing the volume. How much water do we have in this tank at time t? All right, so what does the derivative v prime represent? Well, it represents the rate at which our volume is changing at time t. All right, so we're going to look at what this net change theorem says in relation to volume here, this little discussion. So our net change theorem says if we were to integrate the derivative v prime of t from a to b, well, that's the same thing as looking at the volume at time b minus the volume at time a. So the net change here on the right, this v of b, well, this is just our ending volume, or ending water level. And v of a is just our starting volume. So v of a measures how much water we start with. V of b measures how much water we end with. So if this quantity is positive, what that means, if v of b minus v of a is positive, well then the ending volume is bigger than our starting volume. So more water came in than was lost. If this quantity is 0, well that means our starting volume and our ending volume are the same. So we have some water coming in, we have some water going out, and they're perfectly balanced. There was no change in the volume, no net change in the volume of our water over that time interval. Our starting volume and our ending volume exactly the same. And if this quantity were negative, well, that means v of a is bigger, and that means our starting volume is bigger than our ending volume. So the overall effect during that time interval is that we lost some water. All right, so that's what the right-hand side of this equation represents. Let's think about the left-hand side, this integral. And we're going to think of it in terms of just this little graph here. This is just an example. So let's think about what v prime is doing. So v prime is the derivative. It represents the rate at which our volume is changing at every little instant in time. So what we're doing here is essentially v prime is describing all these tiny little fluctuations in our volume, and we're taking all those little fluctuations, adding them together, and what we're getting is the overall effect over that entire time interval. So v prime is describing, at this one moment, water's coming in, or v prime is describing at another moment, water's going out. So it's taking all those tiny little changes at all those little instants in time, kind of bundling them together, adding them all together. And what this result is doing, what this definite integral is doing, is it's saying, all right, just giving you the net effect, the net change. Our ending volume minus our starting volume. So it's going to be helpful to think of a little example here. So we have this graph for some v prime. And so we've graphed the function v prime. And when v prime is positive, What does that mean? That means the volume is increasing. So the water level in our tank is going up. When V prime is negative, what does that mean? Well, that means the volume in our tank is going down. And when V prime is positive again, our volume is going back up. All right, so, V prime positive means our volume is increasing. This is nothing new. We've looked at this in our optimization section. When V prime is negative, what does that mean? Well, it means our volume is decreasing. All right. But now let's think of it in terms of these regions under the curve. So let's call this right here, we'll call this T1, and we'll call this T2. So let's look at this region right here from A to T1. That region under the graph is above the horizontal axis. So if we know how to calculate the area, if we just think of this as just a curve and we're finding the area under the curve, the area for this shaded region, what does it represent? Well, it actually represents how much our volume increased during that little time interval from A to T1. So if we were to calculate the area for this shaded region, what that represents is it represents how much water, or the volume of water, we increased during that time interval. All right, so calculating the area under that graph from A to T1 represents, well, how much water did we actually increase by during that time interval? We know if V prime is positive, then that means our volume is increasing. So calculating this area really represents how much water we actually increased by during this time interval. Now, if we were to look at this section right here, now this region of the graph is below the horizontal axis. So if we could calculate the area for this region, if we could calculate the area for this shaded region, what this represents is the volume of water that we lost, or that was decreased during the interval from T1 to T2. So for the section here that's below the horizontal axis, if we could calculate the area for this shaded region, what that area represents is it represents how much water we lost during that time interval from T1 to T2. So we know, since V prime is negative, we know that the water level's going down, and if we calculate the area for this shaded region, well, that describes actually how much water did we lose during that time interval. And back over to here, V prime switches back to positive. So our volume starts going back up. And so if we could get the area for this shaded region, if we could get the area for this shaded region from T2 to B, what this area represents is how much water increased. How much did our volume increase during that time interval? So when we have these sections of V prime that are above the horizontal axis, we know V prime is increasing, so the volume is, or we know V prime is positive, so that means the volume is increasing. And by figuring out the area, which we know is related to the definite integral, by figuring out the area for these shaded regions, what we're really doing is we're figuring out, well, how much water or how much did our volume actually increase by during those time intervals. And for these sections where V prime is negative, right here, V prime is below the horizontal axis, so we know the volume is decreasing. Well, if we were to calculate the area for this shaded region, what we're really doing is we're figuring out, okay, how much water did we actually lose during that time interval? So how much did our volume actually go down? So it's kind of interesting to relate this to area under the curve. And that's what we're going to do next with motion in a straight line. So we're gonna think about this very similar setup, but for motion in a straight line. So we'll see you there.